These are in listen-only mode.
Well, good afternoon, everybody. Welcome to this webinar. My name is Claire Francis, and I'm from the organisers at Scientific Update. Just got a couple of points of admin before we get started. Firstly, I'd like to thank our sponsors, Technobis Crystallization Systems. Without them, this webinar wouldn't have been possible, so thank you to them for putting this on. We have about 40 slides to present, which will take between 40 minutes and about an hour. And the slides and a recording of the webinar will be available to you after the session has ended. It might take a day or so for us to streamline that and send it to you via email. Because of the numbers of people attending, we've decided to take questions via email after the session. What we'll do is we'll collate all the emails, ask the presenter to answer them if he can, and then I will send the questions and answers to you afterwards. So without further ado, it's my pleasure to introduce our speaker this afternoon. His name is Joseph ter Horst, and he's a professor at the University of Strathclyde, and he's going to present to us on crystal solubility, importance, measurement, and more. Over to you, Joe. Thank you very much.
Thank you. So I'm Joop ter Horst, and welcome to this webinar. So I'm stationed at the University of Strathclyde, and I have my research group within the EPSRC Center for Innovative Manufacturing in Continuous Manufacturing and Crystallization, so in short, CMAC. So they are and we are investigating the acceleration of the adoption of continuous processing in pharmaceutical manufacturing. And my research group is located within CMAC. So I'm looking with my research group into industrial crystallization. So I'm looking into connecting products, crystalline products, with the process through the phenomena that are occurring in industrial crystallizations. So the topics I'm investigating are, for instance, the fundamentals of crystal nucleation. I'm also looking into chiral resolution, crystallization of chiral compounds. And of course, I'm looking into pharmaceutical and protein crystallization. So industrial crystallization, yeah, you have to look at the solubility of crystalline compounds. So to introduce solubility, we can have a look at phenanthrene and anthracene solubilities. So if you look at phenanthrene and anthracene, they are quite similar. So if you put these molecules in benzene, you would expect that the intermolecular interactions between solute and benzene are quite identical. So then if we measure the solubility, we get quite different numbers despite these interactions being similar in benzene. So phenanthrene has a very high solubility, so it's 20.7 mol%, while anthracene has less than 1 mol% of solubility. And we can have a look at the melting temperature of these compounds, and we see that phenanthrene has a relatively low melting temperature, while anthracene has a very high melting temperature of 217 degrees Celsius. So that indicates that the intermolecular interactions in anthracene are much larger than in the phenanthrene crystal. So it actually says that anthracene prefers the solid phase over the solution phase. And that's why the solubility of anthracene is lower, much lower than phenanthrene. So actually the solubility of a crystalline compound is determined by the intermolecular interactions in both the solution and in the solid. So that's an important information, that solubility is determined by both the crystalline compound and the solution. So we can define a solubility, a crystal solubility, as the solution concentration, so that's the C star usually used, the solution concentration that is in equilibrium with the crystalline solid at a specific temperature and a specific pressure P. So usually the pressure is just ambient pressure. And we need this solubility information to know more about the crystallization process. For instance, the crystallization of pharmaceutical compounds. In pharmaceutical industry, you would start with a synthesis, and you get a mixture after your synthesis, and you want to purify this this pharmaceutical from this mixture. And you can do a crystallization process. Usually a single stage is enough to create a suspension, and this suspension of crystals then can be filtered to separate the crystals from the solution, and you end up with a very pure crystalline product often, and you have a remaining solution which should contain all the impurities and the solvent. So the crystallization process consists of a number of sub-processes. So primary nucleation, so the formation of crystals, and these crystals then grow out to become macroscopically large. And if these crystals are large enough, they might hit the stirrer, so that you create attrition fragments, and that process is called secondary nucleation. And sometimes you see that these crystals agglomerate together to form particles that consist of several single crystals. So this process is governed by say the solution in which it occurs, and say the hydrodynamics, the fluid dynamics that are caused by the stirring, and by the supersaturation that is governing the process. So the supersaturation is the driving force for crystallization, and if you know something about the solubility, you know then something about the supersaturation. And then the crystallization process results in a product quality and a certain amount that you crystallize out. So that I call that the productivity or the yield. And product quality is defined by, for instance, the polymorph you're making, and the crystal size distribution, and then the shape and the purity of the crystalline particles. You can crystallize in a number of ways. So here on this slide I've shown evaporative crystallization. That's on the upper left, where you see a solubility line which is almost horizontal. So that means in the concentration versus temperature plot, your solubility, which is the blue line, hardly is affected by the temperature. So you would have to create your supersaturation by increasing your concentration through solvent evaporation. And in the upper right graph of concentration against temperature, you see a more steep solubility line, which is the blue line, which tells you that the solubility is a function of temperature. So if you would cool down a clear solution, at some point you would cross the solubility line and you could start your crystallization process. So that is cooling crystallization. So another crystallization process is anti-solvent crystallization, where you would use the effect of anti-solvent on the solubility of the compound. So if you add anti-solvent, you would dilute your solution, but your solubility should decrease much more than you're diluting the solution. So that would create a supersaturation and gives you the possibility to crystallize. And then in the lower right graph, you have the precipitation process, where you have a reaction that creates a slightly soluble crystalline material, which then crystallizes out. So you would crystallize, for instance, calcium carbonate or barium sulfate using a precipitation process. So all these crystallization processes are actually determined by the solubility line. So it is very important to know how the solubility behaves as a function of temperature, or as a function of anti-solvent fraction, or as a function of the composition in a multi-component system. To give an example, here is a phase diagram that you could use in a cooling crystallization process. So you start with a clear solution at a high temperature, and you would cool down to a low temperature, and on your way down in temperature you would cross the solubility line and you can start crystallization. And then if you wait long enough after you form your crystals at a certain temperature, you would reach a concentration in the remaining solution which is equal to the solubility at that temperature. And that enables you to calculate, for instance, the yield of your crystallization process. So here I did that here, just a simple example where you see the concentration and the solubility. So we started with a concentration of 100 milligram per milliliter, and at the end of the crystallization concentration process you would be at a temperature where the solubility is 20 milligram per milliliter. So the difference between the two is the amount you can crystallize out from that solution. So that would be in this case 80 milligrams of crystals per milliliter of solvent, and that would be the yield or the productivity. So 80% of your product is then crystallized, and 20% of your product remains in the solution. So that's important to know how much you can crystallize out and how much of your valuable product stays behind in the solution. It may be worth recovering that 20%. So the solubility curve is actually the first step towards a crystallization process design, because it tells you the amount you can crystallize and the amount you cannot crystallize. So it's important to know the solubility. So how do we measure this solubility? The solubility is just the solution concentration that is in equilibrium with the crystalline solid at a specific temperature and pressure. And we can measure that by just making a suspension of crystals in a solution and then leave it for a long time to equilibrate at a certain temperature and pressure, and then take a sample of the solution and analyze the concentration in that solution. And you can analyze that by HPLC or through just evaporating the solvent and weighing how much is remaining. So then you have the orange point in the phase diagram, which is shown on the right. So concentration against temperature. We start at the blue point. That is the composition of the sample, and it equilibrates towards the solubility line, which is the red line, and that gives you the concentration, the solubility. So it can be a very accurate method, but it takes a long time to really establish a solubility curve such as is depicted here. So it's time consuming. We also have a temperature variation method where you would determine the clear point temperature. So then you would start with a suspension at a low temperature, and you just shine light through this sample, and the light is blocked by the crystals. But if you increase the temperature, your solubility usually increases with temperature. So at some point all your crystals will disappear and you will end up with a clear solution at a certain temperature, and that is detected by the light that goes through the sample then. So that would be your clear point temperature. It is the temperature at which a suspension becomes a clear solution during heating with a certain rate. To show that what happens in the phase diagram, you again start with a certain point which represents the overall composition in the sample, and you have a corresponding solubility there, but you're still in the region where you have a suspension. So you would increase this solubility until the suspension turns into a clear solution. And that would be at the purple point in the graph. So it is quite a quick method where you would be able to obtain a full solubility line in about a day. And as a bonus, you would get information on the metastable zone. So here's a typical output from such a measurement. So it's temperature against time, and that's the yellow line. So you would cool down a clear solution, and at some point your transmission of light, that is at the right vertical axis, that is the green line, that goes down at the point so that you have a suspension, and then you can start heating up your sample to higher temperatures, and at some point you would see your transmission become 100%, and that is then your clear point. And you can repeat this measurement again. And then the clear point is indicated by these red circles, and it's at 100% transmission, and the corresponding temperature, clear point temperature, is 42.2, and the second measurement was 42.3 degrees Celsius. So it can be quite reproducible. So this took about 1 day, and if you do multiple samples in one go, you would have a full solubility line in 1 day. I usually use a heating rate of 0.3 degrees per minute, and that is because these crystals need some time to dissolve. So here is the clear point temperature as a function of the heating rate, and if you have relatively fast heating rates, say more than 1 degree per minute, you would measure higher clear points, because then the crystals cannot dissolve fast enough in the measurement. So that's why usually we use about a heating rate of about 0.3 degrees per minute. So we can here identify a saturation temperature, which is which would be the clear point temperature at very low heating rate, and that would be about 42.5 degrees. And that would be really the thermodynamic saturation temperature if your crystals dissolve fast enough, and if your crystal detection limit is low enough, and if you don't have fouling or so crystals sticking to the vial wall, or crowning, so that would be crystals that stick just above the liquid level in your vial. So a good advice would be to not just take the data for granted that is coming from your measurements, but also have a look at the vials and see whether there's something peculiar happening, because all crystalline compounds crystallize differently, and you never know what happens. So a heating rate of 0.3 degrees per minute would be my suggestion. I also prepared some slides on solubility analysis, but I would skip them. I will include them in the slides in the PDF I will provide after the lecture. So I'm going to the solubility measurements in complex multi-component systems. So if you have several components in your system, you might end up crystallizing a compound that consists of several components, like in this movie, where you see suspension of isonicotinamide and carbamazepine crystals. So I just put them in a microscopic vial, these crystals, and then added ethanol to them, and you see already these needle-like crystals appearing, and if the movie works, you see them grow out while the isonicotinamide and carbamazepine dissolve. And it becomes even more complex if you see that the needle-like crystals that grow out in the end also dissolve and give plate-like crystals, which would be the most stable crystalline form. So this is a co-crystal that is formed of isonicotinamide and carbamazepine, and this co-crystal consists of both isonicotinamide and carbamazepine. So the solubility of this co-crystal is also a function of the amount of isonicotinamide and carbamazepine present. And we want to know more about this solubility, and we know that the solubility is a function of temperature, but now it's also a function of the composition of, say, the amount of isonicotinamide and carbamazepine present. So we know the pure component solubilities of isonicotinamide and carbamazepine, which are shown in this graph. And isonicotinamide has a slightly higher solubility, so 6 times higher solubility. And now we can have a look at what is the solubility of the co-crystal system. And we decided to use a different solubility measurement method for that, because we didn't want to have the temperature as an additional variable in this in these solubilities. So we wanted to measure the phase diagram as a function of only the composition in the solution. So what we did is have at a specific temperature and pressure have a suspension to which we added a solvent or a solvent mixture. And then we actually take a suspension in the concentration against the temperature graph, and then we just dilute until we see a clear solution. And the moment you see a clear solution, that say the composition at that point would be your clear point concentration, which is related to the solubility. This solubility measurement is a bit faster than the equilibrium method, but a bit slower than the temperature variation method. But it is very suitable for multi-component systems, so complex systems in which you want to know the solubility. There's actually no limitation to the number of compounds in the sample, as long as you have a point where your suspension turns into a clear solution, then you can measure this point at what concentrations it occurs. So we used the crystalline for these measurements, and we equipped it with syringe pumps, and each syringe can then hold a different solvent composition and can feed into a different vial. And we can have various flow rates. So in the co-crystal example I give for carbamazepine, isonicotinamide and ethanol, we started with a sample composition that is determined by roughly the pure component solubilities. So that's this blue point in the graph of the carbamazepine concentration against isonicotinamide concentration. So this blue point would be a suspension of co-crystals, and then we can dilute with pure ethanol. So we would move towards the 0 point, and at some point we would expect a clear point concentration. So we diluted this sample and ended up at the next point where the vial was completely filled. So we still had a suspension, and then we started the second measurement at the blue point where we had this suspension and diluted again, and then we ended up measuring a clear point concentration given by this yellow point. So that is the solubility of the co-crystal. So that's determined by a concentration of isonicotinamide and a concentration of carbamazepine. And then we took the same starting point and added a solution of carbamazepine. So we move towards the left, and then came across a clear point concentration given by this yellow point, upper yellow point. But we can also take the same starting point to add a solution of isonicotinamide to end up in the yellow point, in the lower yellow point. And in such a way we can actually probe the entire phase diagram of the co-crystal and of the other solids that can crystallize out in this under these conditions. So that was the solvent addition method, so the third solubility measurement method. So of course we can encounter polymorphs during our solubility measurements, and usually so polymorphism is the ability of a chemical compound to form two or more crystal structures. So for instance, isonicotinamide is shown here. It forms needle-like crystals, or more block-like crystals on the right. But it's difficult to know in a solubility measurement with the temperature variation method which form is actually present in the vials. So if we start in a suspension, so concentration against temperature, we start in the suspension region and we heat up until we encounter a clear point, but we are not completely sure at the point of dissolution which polymorph is present. So it's also always important to know that that if polymorphism is an issue, that you might measure different clear point temperatures depending on the solubility, the clear point temperature you are determining the solubility of. So that is an example of polymorphism, and there are a number of different phase diagrams possible next to say the eutectic phase diagram, which is shown in this slide. So A is a relatively normal phase diagram, the eutectic phase diagram. And then for if salts or co-crystals or sulfates are formed, you have a crystalline phase that might contain more components in specific ratios. And it's important to determine what you measure the solubility of. And then towards the right you have phase diagrams of solid solutions, and then the crystal phase might contain more components in varying ratios. So if you have that occurring, that also complicates the solubility measurements. So there was an inventory made on all these phase diagrams and how often they occur. Although it is a relatively old study, which showed that the eutectic phase diagram, say the normal one, occurs in more than 50% of the cases. It is important to be aware of other phase diagrams that might occur other than, say, the simple eutectic phase diagrams. So salts, co-crystals and sulfates might form, but you might also end up with a solid solution if you have complex multi-component systems. To give an example of such say more complex phase behavior, we can look at chiral compounds. So where you have left-handed and right-handed enantiomers, which can form crystals together or just form individual crystals. So we have a racemic compound that in which both enantiomers would be present. That's in the middle, and that has a different phase diagram from a conglomerate system where you would have left-handed and right-handed crystals which contain only one enantiomer. And then you would have a solid solution on the right, which would contain both enantiomers in varying ratios. So also these phase diagrams you can measure solubilities of, and you could actually identify the kind of solid state by measuring the phase diagram. So then we would have a ternary phase diagram because we have both enantiomers present and a solvent. So here is a sample composition given for the system asparagine in water. So in water, asparagine forms a hydrate, and compositions are given on the left, and the clear point temperatures that we measure are given on the right as a function of the solvent-free enantiomer fraction. So we see that in the case of asparagine in water, we see a conglomerate system. In another case, ibuprofen in hexane, we see a big bump in the middle, which indicates a racemic compound. And then for atenolol in ethanol, we see a horizontal line as a function of the solvent-free enantiomer fraction, which indicates a solid solution. So that was measuring solubilities in complex multi-component systems and their issues. And as a last topic, I wanted to tell something about crystallization kinetics. So once you determined the solubility, say the thermodynamics, we can also look at the kinetics. So in a clear point temperature measurement, you would increase the temperature in a suspension until you see a clear point. So that would be around 37 degrees. You see the clear point. And then you would cool down the clear solution again until you see crystals. And then you can determine the cloud point at the point where you detect the first crystals, where the transmission of light is decreased. And actually clear point and cloud point are not the same, and that is because of the kinetics of the nucleation process. You have to overcome an energy barrier to be able to nucleate, and that energy barrier can be expressed by determining the difference between the clear point and the cloud point temperature. It gives you the metastable zone width, that is the region between the clear point and the cloud point. And another way of measuring the kinetics of crystallization is by determining induction times, and that would be the induction time is defined as the time until the detection of crystals at a constant supersaturation. So we need accurate temperature control for that, and this is a typical measurement where we heat up a suspension until a clear solution, until we have a clear solution, and then crash cool it to a low temperature where we know we have a driving force, and then we just wait until the transmission of light goes down, which means we have crystals present in the sample. And the time it takes from the generation of supersaturation to the detection of crystals gives you an induction time. So if we do that for under exactly the same conditions for a large number of measurements, we get this plot on the left where the induction time is plotted as a function of the experiment number. And you actually see that that this induction time varies quite a lot. It varies from say about 1,000 seconds to about 9,000 seconds. And that is because of the nucleation process. It is a statistical process, a stochastic process. So you have a certain chance that a crystal forms, and that chance is actually expressed in the plot on the right, where the probability that you measure a certain induction time or less is expressed as a function of induction time. So the experimental data of the graph on the left is translated to the graph on the right, and from that graph on the right we can now determine a nucleation rate. So we did that, for instance, for a chiral compound in different solvents. So here you see the different induction time probability plots at various supersaturations. And for each plot we can determine the nucleation rate at a certain supersaturation. And that actually indicated that the nucleation rate in one solvent is much faster than the nucleation rate in another solvent at the same supersaturation ratio. So quite valuable kinetic information on crystallizing systems. So that was all I wanted to cover from solubility measurements to crystallization kinetics. So to summarize the presentation, I think I've shown that maybe all crystalline compounds behave differently upon crystallization. We have seen the temperature-dependent solubility of a compound, and that is the first step towards a crystallization process design. We've seen 3 different temperature measurement methods, the equilibrium method, the temperature variation, and the solvent addition method. And then as a last part, we looked into metastable zone with induction time and their relation to crystal nucleation rates. So these are my acknowledgements with all the people that helped me gather all the data and more. And these are all the partners in CMAC that made the research that is performed within CMAC possible. And these are my details. So you see an email address, and on the Google Scholar website you will find all my publications, and in the ResearchGate website as well. And I added some publications on solubilities in this last slide. So here this presentation ends, and I give back to the organizers.